Hello and welcome to the lecture on 4.6. Today we're going to talk about modeling with exponentials. So what we're going to do here is sort of put this into real world context and have problems that we can draw from the real world in order to develop models that involve exponentials. And when we talk about exponentials in particular, generally we see something that looks like this. We start with something, it doubles, and each of those things double as well. And then each of these double. So you can see that the population of whatever these things are actually grows very rapidly. So the next thing I want to talk about is the exponential growth involving doubling time. Now there's two of these that we use. We use the doubling time and we use the relative size growth. And we'll talk about doubling time first. If the initial size of a population is n sub 0 and the doubling time is a, then the size of the population at time t is given by the function n of t is equal to n sub 0 2 to the t over a power, where a and t are measured in the same time units. Let me explain what this doubling time is first. The doubling time is obviously the time it takes for a population to double. But if it's a, then why do we get this equation? N sub 0 times 2 t to the t over a power, like this. So let's suppose we don't know what our population formulation is, and we have something that looks like this, 2 to the kt. I want to figure out what k is and its relevance to doubling time. If the doubling time is a, then what is k's relationship with a? We obviously know that k is going to be 1 over a because that's what our formula says, but why is the formula this way? Well, if n sub 0 is our initial population and we want to see how long it takes to double, we say that a is our doubling time. So t is going to equal a in this case because that's the time it takes for the population to double. So if t is equal to a, then we have 2 times n sub 0 here, i.e. double the initial population, 2 to the k times a, because a is equal to t. That's the doubling time. Now, if we cancel our n sub 0s, then we have 2 is equal to 2 to the k power, k times a power. If we're to then solve for k, because that's what a would be given in the problem, if we're looking for what k actually is and its relationship with a as something that would be given in a problem, then what we would do here is say that k times a is equal to 1, because we have 2 to the first power is equal to 2 to the k times a. And then we can see that k would actually equal 1 over a. So that's where we get this formula for our doubling time. Let's go ahead and do an example. Suppose the loath wolf has a doubling time of 60 years. If they only had a population of 40 100 years ago, how many loath wolves exist today? Well, since we know what the doubling time is, we know what our a is. A is equal to 60, and it's in years. So our t is also going to be in years. We also know the initial population, which is n sub 0, and that is 40. There was a population of 40 100 years ago. Now t is going to be 100 because we are preparing this model using a starting point of 100 years ago, and we're looking at the population today. So how many loath wolves exist today? First, let's set up the model, and this will be n of t. The population will be 40 times 2 to the t divided by a, which is 60. Now we have t over a because it's n of t. We are looking for n of 100, where our t is equal to 100. So we get n of 100 is 40 times 2 to the 100 divided by 60. And of course, we get 40 times 2. This ends up reducing to 5/3. So we have this. We just need to resolve this from here, and we will be set. And we end up with a population of roughly 127. Try one. Find the function that models the population of the Kowakian monkey lizard if the initial population is 5,000 and the doubling time is 60 years. So all you're doing here is actually looking for the model. You don't actually need to find an exact population. You're just trying to find the model. The next thing I'm going to talk about is exponential growth with relative growth rate. Note, the relative growth rate is the percentage of the population that is added to the population continuously. This should trigger something in your brain about continuously adding something to the population. Now, it should remind you of continuously compounding interest when we have that. So these formulas are actually going to be very, very similar because continuously adding a percentage of the population to the population is the same thing as continuously compounding interest at a specific rate. Exponential growth. A population that experiences exponential growth increases according to the model n of t is equal to n sub 0 e to the rt, where n of t is the population size at time t, n sub 0 is the initial size of the population, r is the relative rate of growth, and t is time. So let's go ahead and do an example of this. As I said before, this should look very similar to the continuously compounding interest formula that we had, where your principal would be your initial population, your rate that you're compounding is going to be the rate of growth for our population. T is the same, it's time in years. And you still have this E here because it's a continuously compounding, just like you're continuously adding to the population. Example. The Geonosian population will grow by an estimated 3% per month over the next 5 years. Find the estimated population growth of the Geonosians 5 years from now if the current population is 40. So here, remember, we're continuously, we have a population growth rate of 3%. So we're continuously adding that 3% every single moment. So we're going to have the form n of t is equal to n sub 0 e to the rt. Our rate is 3%, which is the same thing as 0.03. Now we have to be careful here. Our n sub 0 is equal to 40. Now we have to be careful here with our t because our rate is per month, but our t we're looking for in years. Those two need to be the same time units. So we have months when we're talking about the rate, and we have years when we're talking about time. So we need to convert one of them. It's easier to convert t. So we're going to convert t, 5 years, into months. So how many months is 5 years? Well, there's 12 months in a year. For 5 years would be 60 months total. So t will equal 60 months. This is where we have to be careful with our units, because as I said before, you need to have a common unit between a and t in the previous model, and your r is going to be a percentage per some time unit, needs to match the t in this model. So here we have n of t is going to equal n sub 0 e to the 0.03t, and then we're looking for n of 60 because 60 months is 5 years. Our n sub 0 is 40. We have 40 e to the 0.03 times 60, like this. And the estimated population after 60 months or 5 years is 242. Next thing I'm going to talk about is radioactive decay. Here we discuss the same model except mass is decreasing instead of population increasing. Definition. The half-life is the time it takes for the sample of the substance to decay half of its original mass. So this is actually what we use in order to carbon date things. So if we have something, we check how much carbon it currently has, and we do a prediction of how long it's been here based on the amount of remaining carbon. If m sub 0 is the initial mass of a radioactive substance with half-life h, then the mass remaining at time t is modeled by the function m of t is equal to m sub 0 e to the negative rt, where r equals ln of 2 divided by h is the radioactive decay rate. So in this model, we start with m sub 0 mass. And then over time, that mass is going to reduce just by radioactive decay. So it's just going to continually reduce at some rate, r. Now, as it decays, we get less and less of this mass. And if we know the end result, how much mass of this object is left, then we can figure out how old it is based on how much mass that object is supposed to have. What I want to do next is sort of derive this formula a little bit, just a little bit. So note, we're going to start with m of t is equal to m sub 0 2 times negative t over h. So this is the same model with half-life h still, but we have it in terms of t now. So note here that if we have a half-life of h, then when we plug in h for t, we should have half of our mass remaining. And we can easily verify that with this. So m sub 0 to negative h over h will give us 2 to the negative first power, which is the same thing as 1/2. So this would be 1/2 m sub 0. So after h units of time, however many units of time it is, after that many units of time, we would have half of the original mass left. Okay, so this is the model that we can use. But let's use this model instead, because this is the model we mostly use. M sub 0 e to the negative rt. Now what I want to do here is figure out what r is relative to h. So we need to figure out what r is relative to h. So again, h is the half-life. So I'm going to plug that in for t, and I should have half of the mass remaining. Now I want to solve for r so that I can know what r is relative to h, just in case I need it. So 1/2 of m sub 0 will equal m sub 0 e to the negative r times h, because we're plugging in h for t. It's the half-life. So it's the length of time it takes for the mass to decay to half of its original mass. We can, of course, cancel our m sub 0s, and we're left with 1/2 e to the negative rh. So again, I want to solve for r. So I take the ln of both sides, and I get ln of 1/2 is equal to negative rh, and then I just divide by h. I divide by a negative h, so I end up with negative ln 1/2 divided by h equals r. Now, what I want to do next is move this negative to be a power on the 1/2, which will then be r is equal to ln of 1/2 to the negative 1 power, all divided by h. And if you remember what a negative power does, is it'll flip the fraction. So we'll end up with r is equal to ln of 2 divided by h, where h is the half-life of the substance. Now the half-life of each substance is different. For some, it's very short. For others, it's very long. We use carbon-14 most of the time when we carbon date, because its half-life is roughly 5,700 years. So it's quite a long time. So now that we have our r, if we're given a problem with half-life, we can just plug it in as if we know what our R is, because we know what the R equation is. This is what R is relative to the half-life. Now let's do an example now. Doug scientists unearth a Zillobeast fossil. If the bones contain 20% of the original carbon-14, how long has the Zillobeast been dead? Now, as I stated before, carbon-14 has roughly a half-life of 5,700 years. It's 5,730 years. So this is what our H is going to be. Now again, it's different for each substance. So if you're not using carbon-14 and you're using some other molecule, then you'll get a different half-life. So here H is 5730. And our R, of course, is equal to ln of 2 divided by 5730. And what we're looking for is how long it's been dead if we only have 20% of the original carbon-14 remaining. So, what are we looking for? We're looking for how long it's been dead, which is a length of time. So we're looking to solve for t. Now, this is where a lot of students will get hung up. They don't really know what the original amount is. It's not given in the problem. So you shouldn't know. What's important, though, is that 20% of that original amount is remaining. So our model, m of t, is still going to be m sub 0 e to the negative rt, but this is going to remain unknown. We do know, however, how much is remaining. 20%, so 0.2 is 20%, of m sub 0, the original amount, is going to equal m sub 0 e to the negative ln 2 divided by 5,700 times t, like this. So this is what we have left. We have 20% of the original amount. It's equal to the original amount times this decay model. So we can divide both sides by m sub 0, and it cancels out. Like I said, the original amount is unknown, but it doesn't matter because it'll cancel out in the end. We take the ln of both sides. We end up with ln of 0.2 here on the left, and on the right, this is all an exponent. So when we take the ln, the e and the ln sort of cancel out, and we're left with 1 over 5730 times t times ln of 2. And we have a negative here. So solving for t, we get t is equal to 5730 ln 0.2 divided by, I have a negative here, divided by ln of 2. And t is roughly 13,305 years. So this Zillobeast has been dead roughly 13,000 years. The last topic I want to cover is Newton's law of cooling. If d sub 0 is the initial temperature difference between an object and its surroundings, and if its surroundings has a temperature of T sub s, then the temperature of the object at time t is modeled by the function capital T of t is equal to T sub s plus d sub 0 e to the negative kt, where k is a positive constant that depends on the type of object. Okay, so there's a lot here, but specifically the model is what we're going to use to show the cooling off of temperatures. This one I'm not going to end up proving because, frankly, I don't know the proof of this one. But d sub 0, you do need to know. I'm going to write this over here. D sub 0 is equal to the temperature of the object, let's say T sub O, minus the temperature of the surrounding atmosphere, whatever it is, temperature of its surroundings. Let's go ahead and do an example, and maybe this will help a little bit. A cup of blue milk with temperature 30 degrees Celsius is put into a refrigerator where the temperature is 15 degrees Celsius. After 20 minutes, the milk is 25 degrees Celsius. Find a model that models the temperature of the blue milk at time t. So there's a few things we need to find first, specifically t sub s, t sub 0, and k. Now, k is going to be the hardest thing to find because k is dependent on the type of object that we have. T sub s, so think about it, we have a cup of blue milk that's sitting out, and then we put it in the refrigerator. So the refrigerator is 15 degrees. So T sub s is 15, it's the surrounding air. T sub 0 will be the temperature of the object minus the temperature of the surrounding air. And in this case, T sub O is 30 degrees because that's the temperature of the blue milk when we put it in the refrigerator. And T sub S is 15 degrees, as we stated here. So this would be 30 minus 15, which is equal to 15. So D sub 0 is going to be 15 as well. Now, we need to figure out K. And we haven't used 25 yet. We'll get there in a second. So T of T, as of right now, is 15 plus 15e to the negative kt. Now we need to figure out what k is. And this is where we're going to use the 25. So after 20 minutes, so if we let t be in, t is time, and I'm going to say that it's time in hours. Okay. So after 1/3 of 1 hour, so when t is equal to 1/3, the milk, T of t, is equal to 25. Right? So we have a point. I'm going to rewrite this to state it a little bit more clearly, hopefully. T of 1/3, so when t is 1/3, is equal to 25. So the temperature of the blue milk 1/3 of an hour after we put it in the refrigerator is 25 degrees. Okay, this is how we're going to find K. So we plug in 1/3 and we get 25. So 25 will equal 15 plus 15e to the negative k times 1/3. Again, t is 1/3 in this case. Now we just need to solve for k. So we subtract the 15 over, we get 10 is equal to 15e to the negative k over 3. Divide by 15, and we get 2/3 is equal to e to the negative k over 3 again. Now, in order to solve for a variable that is in the exponent, we need to take a logarithm. So we're going to take the ln of both sides to completely eliminate the e, because the ln is the logarithm with base e. We take the ln of both sides. And on the right, when we take the ln, the e cancels, and we're left with just negative k over 3. So multiply by negative 3, and we get a negative 3 ln 2/3 is equal to k. So now that we have our k, we can write the model. Now I want to ask you a question, because in the previous statement, we talked about k being a positive constant. So when we look at this, is k a positive constant? Now you have to think about this for a second. Don't just say the first answer that comes to mind. Actually look through it and think about it. This is actually going to be positive. The reason is ln of 2/3 is in fact negative. So we would have a negative times a negative times 3. So this is actually a positive value. What I'm going to do is I'm going to move my negative 3 up here to be an exponent. So we can rewrite this as k is equal to ln of 2/3 to the negative 3 power. And then we can move this negative 3 to be on both of these because we're dividing both of these bases. And we end up with ln of 3 to the 3rd, which is 27, divided by 2 to the 3rd, which is 8. And we're done. Notice that I also changed the positions because I have a negative value in my exponent. So this would have been 2 to the negative 3 divided by 3 to the negative 3. Now it's 3 to the third divided by 2 to the third. So here's my k value. Now I can write my model. We get t of t is equal to 15 plus 15 e to the negative ln 27 over 8 times t. Try one. Now this try one problem is actually very challenging. A clone trooper is found dead on Umbara. His body temperature is immediately taken and found to be 80 degrees Fahrenheit. The temperature of the surrounding air is a constant 68 degrees Fahrenheit. If the body temperature is taken exactly 1 hour later and is found to be 78 degrees Fahrenheit, find how long the clone trooper has been dead initially. Assume that clone's original body temperature is 98.6 degrees Fahrenheit. So I'm going to give you a couple of hints here. Use the 80 degrees, 68 degrees, and 78 degrees to find k. Just like in the last problem, you're going to use these values. Your final answer should be negative. This refers to the length of time before the body was initially discovered. If everyone had alibis all night, with the exception of Dogma 3 hours prior to the body's discovery, Fives 8 hours prior to the body's discovery, General Krell 5 hours prior to the body's discovery, and Oddball 7 hours prior to the body's discovery, who killed the clone in question? All right, that's going to be it for tonight. I will see you all in the next lecture.